we're going to do a review here. And just as a quick note, the exam is multiple choice, which means all of our answers would be decimals and not fractions because it's hard to make sure everyone has the same fraction answer. So just get in the practice of changing everything back to decimals instead of fractions for these chance and probability questions. So a child has 6 packets of candy remaining from Halloween, 3 Snickers, 2 M&Ms, and 1 Kit Kat. The child decides to choose packets at random to eat each day. Obviously, this child is choosing without replacement because she's eating them. So what's the chance that the first choice will be M&Ms? Well, there are 2 M&Ms out of a total of 6, so 2 out of 6. I can put this into my calculator as 2 divided by 6. If you don't remember how to change it back into a decimal, 2 divided by 6, which gives me 0.3333. Okay, my next one. What is the chance that the first choice will be M&Ms and the second choice will also be M&Ms? Anytime you have an and, you're going to multiply your probabilities. So like the probability that I'm going to get an M&M and then another M&M. Let's see, the first day I have 2 M&Ms out of a total of 6. But the second day I've eaten one of those M&Ms, so now I only have 1 M&M left to choose from, and there's only a total of 5 because again I ate one. So this would give me 1 out of 15, or if I just put it straight into my calculator, I should have gotten 0.066. Let's see, what is the chance that neither of the first two choices will be Snickers? So now we're actually looking for the probability that we get a not Snickers and a not Snickers. Well, let's see, if we have 3 Snickers and 6 total, that would mean there'd have to be 6 minus 3 not Snickers. So there are 3 not Snickers the first day, but the next day I've already eaten one, so there are only 2 that are left out of a total of 5. Putting this in should give me 0.2. What is the chance that at least one of the first 2 choices will be Snickers? Anytime you see this at least one, you're going to use the complement rule, which says that the probability of at least one Snicker is equal to 1 minus the probability of no Snickers. Well, how would you find the probability of no Snickers? Well, no Snickers would mean you'd have to have a not Snicker and a not Snickers. But wait, we just found that up above. That was this part right here, 0.2. So 1 minus 0.2 gives me 0.8. And what is the chance that by day 6, the only package left is the Kit Kat? Well, let's just double check here. How many Kit Kats did we have? There was only 1 Kit Kat. So we had 1 Kit Kat and 5 not Kit Kats. Okay, so by day 6, we want the Kit Kat to be left, which means we have to do everything that is not Kit Kats first. So the probability on day 1, so day 1 would have to be not Kit Kat. And day 2 would have to be not Kit Kat. And day 3 would have to be not Kit Kat. And day 4, not Kit Kat. Day 5, not Kit Kat. And day 6, finally, we want to have the Kit Kat. So let's see what this would be. Let's see, so the first day, not Kit Kat, we start with 5 not Kit Kats. So the first day we'd have 5 out of 6 that are not Kit Kats. But the next day we ate one, so we have 4 out of 5. The next day we ate one, so there's 3 out of 4. The next day we ate one, and there's 2 out of 1. Things that were not Kit Kats. Sorry, 2 out of 3. And the last day, on day 5, is our last day of not Kit Kat, so that's 1 out of 2. So all of these are our not Kit Kats. Then on the last day, there's only one Kit Kat left, and there's only one choice left because we ate everything else. And so this day is our Kit Kat. Putting this into my calculator, we should get 1 out of 6 or 0.1666. Okay, next, for each of the following, answer true or false. And it looks like we have a variety of things in here. Okay, so for confidence intervals, we do not need the tickets in the box to follow the normal curve, provided we have a large enough simple random sample. So this one is true because averages and percentages will follow the normal curve no matter what the individual data looks like if the sample size is large enough. Which is just one of those really cool things about statistics that just kind of happens to work. They would also follow the normal curve if your data originally looked normal. This next one, the law of averages says that if we toss a coin more and more times, the percentage of heads will get closer and closer to 50%. Assuming it is a fair coin, yes, this is true. Okay, so the law of averages says the more times you do something, if you do it lots and lots of times, you'll get closer and closer to your expected value. It says if you do something many times, you get closer to the expected value. C says for a large sample, the sample itself, this means when it says the sample itself, it means the actual data or like the individual values. Will follow the normal curve even if the tickets in the box do not. Okay. This is absolutely false. Because if the population is not normal, then the individual values will not be normal, no matter what the sample size. Okay. So again, if the population is not normal, the individual values in the sample will not be normal either, no matter what the sample size. What is it that actually becomes normal? Okay. The individual values don't. Okay. The sample data itself doesn't. If you looked at the histogram of the sample data, it wouldn't be. It is only the sums, percentages, and averages that are guaranteed to be normal for large sample sizes. Okay. So again, the individual values in the data don't have to be normal. It's only the sums, percentages, and averages that have to be normal. That's always a question we like to put on exams to see if you understand that. And D says, for a large sample, the average of the sample will follow the normal curve, even if the tickets in the box do not. Okay. And again, that's the same thing that we did up in the first part. So true, for a large sample size, the possible averages will follow the normal curve, no matter what the population looked like. Okay, in each of these cases, circle the correct answer. This is coming back to that law of averages. So let's just make a note of that here, so you can look it up if you need to. So in each of the following cases, circle the correct answer. A die will be rolled some number of times, and you win $1 if it shows a 6 more than 20% of the time. What's better for you, 60 rolls or 600 rolls? Okay, I think all of these are talking about expecting 6s, so let's just make a note. We would expect to get a 6 on a die. Well, how many times would you expect to get it? There are 6 numbers, so you should expect about 1/6 or 0.1666, or if you want to change it to percent, you can times it by 100%. Move the decimal 2 places to the right, so that's 16.66% of the time. Okay, so if we roll a die, we're expecting to get 16.66% heads, or 6s. Now, in the beginning, I might get a couple 6s, so I might be kind of high, but then I might miss 6s for a little while, and then I might get more 6s, and I might go up, and I might go down, and I might go up and down and up. And in the beginning, you're very wild and fluctuating just because there's a lot of randomness. But the law of averages says that the more time we do this, eventually, we might go up for a little while, you might go down for a little while, but eventually we're going to get closer and closer and closer and closer to this line. Okay. Because if we do it thousands and thousands of times, we should be very close to that 16.66%. Let's see now what we're trying to get. We want to see more than 20% of the time. Okay, so here's my 20%. I'm looking to get above it. Okay, so when am I going to be above that line? Well, I'm only going to be above that line in the beginning. So here's my 60 rolls. Here's my 600 rolls. So when are we going to be more likely to get something wild and extreme that we shouldn't really be getting? It would be at the beginning when our results are still more wild and extreme. So we'd be more likely with 60 rolls. Okay, so next one is, we're still starting at the exact same situation. We still have 16.66%. We'll fluctuate at the beginning and eventually even out. 60 would be here at the beginning. 600 be up here. Now let's see what it wants us to find. Let's see, we win $1 if it shows a 6 more than 15% of the time. Okay. So here's my 15%. Actually, I don't think I put that quite high enough to really demonstrate. Let's say here's my 15% because that's pretty close to 16. Okay, so when are we going to be above that? So we want to be above that. Well, I'm above it sometimes here, but sometimes I also dip down below. If I want to guarantee to be above it, if I come out here, I'm kind of guaranteed to be above it because I'm going to be at 16%. So I'm more guaranteed to be above it out here at 600 rolls. Next one, same thing. You can fluctuate wildly at the beginning and then you even back out. So here's my 60 rolls. Here's my 600 rolls. Okay, now I want to be between 15 and 20% of the time. So here's my 15%. Here's my 20%, and we want to be in between them. So again, over here, I am in between most of the time, but sometimes I do dip below and sometimes I might even dip above. This isn't really drawn to scale. But I know that if I come out here, I'd be guaranteed to be in between because I'm going to be really close to 16%. Maybe not truly 100% guaranteed, but very, very likely to stay within that because I should be at 16.6%. So that'd be between 15 and 20. So I'd be more likely at 600 rolls. Next one. A die has been rolled 10 times, and the last 10 rolls have all been 6s. That does seem very unlikely, right? to get 6s on 10 rows, the chance that the next row will be a 6 is, okay, and we are assuming it is a fair die. In this class, we always assume it's a fair die unless they tell us otherwise. Okay. So assuming it is a fair die, well, a die is supposed to be independent. So they do not affect each other. So no matter what I have rolled already, the chance of the next die being a 6 is still exactly 1/6. So that was just very wildly unlucky, or very wildly coincidental that we rolled 10 6s in a row. But the next one, the probability of 6 should still just be 1/6. We don't really have to worry about like our luck running out or us being on a roll. That doesn't really matter. That's just all coincidence. Okay. Number 4 says, a sample of 5,000 will always be more accurate than a sample of 1,000. It makes no difference how the sample is chosen, true or false. This one would be false. Okay. Well, first of all, it is asking, it's saying, are big samples always better? Well, that would be false with the way they said it, because big samples are better if they are well designed. But a crappy big sample is worse than a small good sample. So it's all about the quality. Having something that's really, really big, but if you did it crappy, it's not going to give you good results. It doesn't matter how big it is. So it's much better to be well designed. But again, just to reiterate, if they are good samples, if they are both good samples, then bigger is better. And good samples are somehow probability based, like a simple random sample. Next one. In the 2008 election, 63% of Utah voters voted for McCain. If we take a simple random sample of 300 of these voters. Okay, let's stop here and think about what it told us. So it's telling us that all the Utah voters, that's the population. So this is telling us that our population percent, my population percent equals 63%. Okay, it's telling us we're taking a simple random sample. So our sample size equals 300. And now it's saying what will happen if you take the sample. So this is one of those problems where we know things about our population and we're going to try and guess what would happen when we take a sample. Let's see, so what percent of our sample would you expect to have voted for McCain? Give or take how much? Well, to expect to have voted, that's kind of our expected value. So the expected value for a percentage, we can use our shortcut formulas and say, well, that's just equal to our population percentage. Simple, easy, we're done, 63%. Our standard error is our give or take amount. So the standard error is equal to the square root of the population percentage times 100% minus the population percentage all over the sample size. So this is going to give me the square root of 63 times 100 minus 63 over 300. Make sure you have parentheses around everything inside the square root. And it's 2.78%. So this means we would expect about 63% of the people in the sample to have voted for McCain. Give or take 2.78%. So there's probably about 63%, but it might be give or take about 3%. So somewhere probably between like 60 and 66% is what we'd expect to have voted for him. Now let's see, what is the chance? Now when you see this, like, what is the chance? That means we're going to have to use a normal curve. So what's the chance that fewer than 50% in the sample voted for McCain? So we're looking for the chance that the percentage is less than 50%. So anytime you want to find this chance and you've started talking about populations and samples and percentages and things, you know you're going to be using the normal curve. And to use the normal curve, you have to standardize, you have to find your z-value. Our formula is it's going to be the percentage minus the expected value for the percentage over the standard error for the percentage. So the percentage we're interested in is 50%. The expected value is 63, and the standard error is 2.78, which gives me negative 4.67. If I was to draw this out on my normal curve, remember z is always centered at like 0, and by the time you get to 3, you're pretty far out in the tails. So for negative 4.67, and you're looking for the area to the left of that, we're doing left because we said less, so we go to the left. That area is going to be pretty small. In fact, if I was to open the normal table, at z equals 4, our area, or negative 4, our area is already 0.0032. We're even smaller than that. So if you are off the chart, you can just say about, the squiggly equal sign means about 0%. It's going to be really small. So about 0% chance that fewer than 50% of people in our sample voted for McCain. Number 6, a department store prints a website on every receipt, and the sales assistants are instructed to encourage customers to go online and complete a survey about their satisfaction with their shopping experience. I don't know about you guys, but I never want to go do those. Let's see. So would this give a simple random sample of all people? No, this is only people in the store, and they had to buy something, and they have to actually go online and take survey. Okay. Well, would it be considered a simple random sample of people that purchased something? Again, no, because, okay, yes, they did go into the store, they did buy something. That took off our first two concerns, but they still have to have internet and computer/phone and carry enough to bother taking it and remember to take it and not lose the receipt before they get home, etc. So there's a lot of things how you can see this is a very small percentage of people that are actually going to be taking the survey. Okay, and it's definitely not a simple random set of people, it's just the specific people that remembered and cared enough to do it. So, would you trust the results of this survey as a measure of how satisfied customers are? Okay, no, because people who take the survey are usually different than people that don't. So usually only people who are really satisfied or really dissatisfied bother taking surveys. And just as a note, remember that unsatisfied people are even more likely to take this survey than really satisfied. So this chart came from the Statesman a really, really long time ago. And you can see here that it's saying, like, who are you going to vote for president? And it had the percentage of people that were going to vote for these different candidates. And then it told you how many actual people that was and not just the percentage. Let's see. So we could add up the number of actual people. So 1662, 722, and 1. That was 134 people. So let's assume that these 134 people are a simple random sample of all USU students. And let's find a 90% confidence interval for the percentage of USU students who were planning to vote for Obama at the time of this study. Let's write a few notes to ourselves. We know that our sample size equals 134. We want to find a 90% confidence interval. And anytime we already have the sample and we're trying to go back to the population, that tells us we're going from sample to population. For me, knowing that I'm going from the sample to the population kind of helps me remember, like, figure out what I'm trying to do. Let's see, what else did it tell us? We want to know how many people were voting for Obama. So here's Obama at 46%. So that means my sample percentage equals 46%. Okay, now let's start. Anytime you want to find a confidence interval, we're always going to do basically our estimate. The general formula is estimate plus or minus Z star times the standard error. That's the formula that you'd see on your cheat sheet. If we're talking about percentages, well, how do you estimate your population percentage? It would be your sample percentage plus or minus Z star times standard error for percentages. Well, let's see. We need to find all those things. We know our sample percentage. We found that. So let's find Z star. I do that by drawing a normal curve and saying, okay, I want to have 90% in the middle. Now my percentages have to add up to 100. So 100 minus 90 is 10. And I have to split that on two tails. So that gives me 5% for each tail. My table gives me areas to the left, so I'm going to try and figure out what Z value would give me 5% to the left. So come back here, look for the areas now. You need an area, which is in the second column, of 5%. Looks like we're really close here at Z equals negative 1.65. So this would be negative 1.65, which means this would be positive 1.65 because it's symmetrical. So I could say that Z star equals 1.65. Now, for your standard error, because we need standard error. Standard error for percentages is always this long formula. It's that square root of population percent times 100% minus population percent over sample size. So square root of, let's see, again, my sample percentage. Oh, wait, I just remembered I don't even know my population percentage. I wrote that down out of habit, which is good. So remember, oh, wait, we don't even know our population percentage, so we're going to estimate it. We'll use our little lines for about. It will be about equal to our sample percentage times 100% minus the sample percentage, because our sample percentage is our best guess for our population percentage, so we'll just estimate it over our sample size. So again, this is about, we don't really know for sure what it is. Square root of, let's see, our 46% times 100 minus 46 over 134. Don't forget to put parentheses around everything inside of that square root. So you should get 4.3%. And I'm just going to make a little note here. Of my best estimate. Let's see, like my best estimate is that 46% of all USU students plan to vote for Obama, but I'm probably off by about 4.3%. Okay, so that's your give or take. One standard error is your give or take, because you always give or take one standard error. But that's just saying like, okay, well, I'm probably off by about that much, but sometimes we like to be more confident. Okay? So instead of just doing one standard error, we might go out to like 2 standard errors for a 95% confidence interval. Or in our case, we just wanted to be 90%, so we're actually going to go out 1.65 standard errors. So that's what we do next for our actual confidence interval. So our confidence interval, again, I'm going to actually just use the formula that you would see on your cheat sheet for the exam. So it is your estimate plus or minus z star times the standard error. So remember, our estimate, that's our sample percentage. So we were estimating 46%. That's your sample percentage. So we're estimating 46% plus or minus z star, which is 1.65, times the standard error of 4.3%, which should give me 46% plus or minus 7.095%. So that's 38.905%. So remember, you subtract it first for 38.9, and then you add it 53.095%. And you should always practice interpreting your confidence interval, because that can always end up on the exam too. I always like to throw that on. So we are 90% confident that, now you can either say population percentage or percentage of all, but you do have to have the words percentage, and you have to have either all or population in your interpretation. So that the percentage of all USU students that plan to vote for Obama is between 38.905 and 53.095%. Now suppose that this was not a simple random sample like we said assume first. Suppose that these came from an online poll. So let's give 3 different reasons why our confidence interval would be unreliable. Okay. So remember, anything that's not a simple random sample is going to be bad. So a few reasons. Our formula only works for simple random samples. And this is not a simple random sample. What are some possible sources of bias? Remember, we first learned about bias in the terms of it affected everything the same way. So these aren't like things because you had a measuring tape, a physical device, but this is like, would we sample something in a certain way that it gets biased in a certain direction? Well, here's some possible sources of bias. Let's see, people first have to go to the state's men's website. I don't know about you guys, but when I was there at USU, I never really went to the website. I read the newspaper sometimes, but I didn't go to that. So you have to have internet, which I know is becoming less and less of an issue now. And you have to go to that site and stay long enough to read the article / poll. Let's see, find the poll and care enough to vote. So this is going to be a very small selection of USU students that truly care enough to go vote. And we're interested enough to happen to find this poll. So here's just like a one way that you could be biased. Okay, so let's just say if only sorry, so if only distance, now I'm not saying it's only distance, it's just that this is like a possible way the bias could happen. So let's say if only distance students go to the online statesman. Sorry, I have a really tiny keyboard I have to use when I'm doing the videos. It's hard to type on it. If they go to the online statesman, then the distance students might be older, most have jobs or families, and so they would probably vote differently than the students on the Logan campus. Okay, next problem. The average GPA for graduating seniors in a large university is 3.13 with the SD of 0.7. So I want to take a simple random sample of 100 graduating seniors from this university. So looking at this problem, I need to figure out a few things. So first of all, it looks like it's telling me that this is the average GPA for all the students. So it sounds like we already know the population information, and we're going to be going to the sample. So it's telling me my population average equals 3.13, and my population standard deviation equals 0.7, and my sample size equals 100. And so it's one of those problems where we know our population already, and we're trying to figure out what would happen if we take a sample. Let's see, so first, what do you expect the average GPA in the sample to be? Well, the expected value for average is super easy because it's just equal to your population average. So 3.13. Part B, your answer to A is likely to be off by how much? So it's asking, what is your standard error? What is the give or take? So your standard error for an average is always equal to your population standard deviation over the square root of your sample size. My population standard deviation is 0.7. My sample size is 100. This gives me 0.07. So we would expect my we'd expect my sample average to be about 3.13, give or take 0.07. Now let's find a chance that the average of the GPA of those in my sample will be more than 3.5. So we're looking for the chance that we're more than 3.5. Again, anytime you're looking for a chance for your averages, percentages, you know, populations, you're talking about samples, that's all going to come from the normal curve. And to use the normal curve, you have to standardize. So Z is going to be equal to your average minus the expected value of your average over the standard error of the average. So the average I'm interested in is 3.5. The expected value is 3.13. And my standard error is 0.07. Put all this in and it gives me 5.28. Let's see. So the normal curve is centered at 0. We get up to here about 3. So here's 0. 3 will be at the ends of your tails. And so by the time you get to 5.28, there's going to be almost no area to shade. Okay. And it's basically going to be about 0%. It's just coincidence that both of these review problems have been about 0%. So final answer, about 0%. If we were to find out that the histogram for those GPAs do not follow the normal curve, is our answer still valid? Actually, I should probably change that slightly. The answer to A is just our expected value. That actually does not change based on the shade. So that wouldn't actually be affected. So let's change this to be what we actually want it to say. Would our answer to part C still be valid? Sorry, I'm not quite sure where I got cut off. I think it was probably about here. Okay, so in the answer to part C, we're saying, well, it tells the individual data in the population is not normal, but because it's a large sample size, the possible averages will be normal, so we can use the normal curve. And then I came in here and I'm guessing I probably missed all of this. So it tells us for a simple random sample of 400 cash value 6-year-olds, the average height is 117.25 with an SC of 4.2. So that tells me that we're talking about a sample. So we have a sample size of 400, a sample average of 117.25, a sample SC of 4.2, and we know that we know our sample and we're trying to estimate our population. So when it says, what is your best estimate for the average height of all your cash value 6-year-olds? Well, the best estimate for your population average is always going to be your sample average. So our best estimate will be 117.25. Now, how much is your estimate likely to be off by? Is asking what is that give or take. That is your standard error. So the standard error for your average is equal to your population SD over the square root of your sample size. But you might say, wait, we don't know the population standard deviation. That doesn't make any sense. I can estimate the population standard deviation with my sample standard deviation over square root of sample size. Okay, so my sample SD is 4.2. Oh, sorry, this is still about because we're estimating over square root of 400, which gives me 0.21 centimeters. Okay, so my best estimate for all the 6-year-olds is 117.25, give or take 0.21. But we might just not want to do just one give or take. We might want to be more confident by going out to 2 confidence intervals, or 2 standard errors with a confidence interval. So find a 95% confidence interval for the average height of all. Remember, all is for our population. Now, on your formula sheet for the exam, it will say estimate plus or minus Z star times the standard error. That's the general formula. If we're talking about averages, it would specifically be the sample average plus or minus Z star times standard error for the average. Let's see, I know my sample average is 117.25 plus or minus. Now Z star for 95%, we just have that memorized as 2. You could look it up on your table to be more precise, but for this textbook, they love to tell you that it's 2 all the time for the 95%, and so we just kind of memorized it. And standard error is 0.21. So this gives me 117.25 plus or minus, let's see, 0.42. So 116.83 to 117.67. And you should always interpret anytime you do a confidence interval. Let's say something like, we are 95% confident that the population average for all the cash 6-year-olds is between 116.83 and 117.67. Okay. Now, what does a 95% confidence level mean? So that's we interpreted our confidence interval. What does the actual 95% mean? What does it mean when we say we're 95% confident? That means when we pick a sample, there are thousands or millions of different samples we could have chosen. And each sample gives a different sample average and hence a different confidence interval. So what we know is that 95% of those confidence intervals contain the true population average. And we hope that our confidence interval that we calculated actually is one that contains the true population average. So is there any way to tell if your confidence interval contains the true population average? No. We don't know. We don't know whether it's one of the 95% that do or one of the 5% that don't. Like, we just don't know. We hope, because 95% that do, so there's a pretty good chance that ours does. Okay, because, let's see, we just hope because 95% do contain it, and we hope ours is one of those, which is a pretty good chance, but we don't really know for sure. Okay, the next one is true or false. There's a 95% chance that the population average is between 116.83 and 117.67. Okay, so true or false? Is that true? The answer is no. Please don't say that. Okay. We don't talk about chance for the population average because it is fixed. It is not changing or random. We just don't know what it is. Okay. I think I will actually add in one more problem here for you. Okay. Just to help you study. Okay, so true or false? 95% of the 6-year-olds have heights between 116.83 and 117.67. So would that be true or false? This would also be false because it's talking about the individual heights. And the confidence interval is always for the average, not the individual data. Plus, it just doesn't actually make sense. How could you have all of your 6-year-olds be only, I mean, look at that, that's only 1 centimeter difference. All of your 6-year-olds obviously are not just within 1 centimeter difference. So when you look at something like this, imagine it this way. So if we were to look at the actual data, so the data of the actual heights look like something like this. I happen to know that heights almost always follow a normal curve, so that's why I drew a normal curve. So the actual heights would be something like this. It'd be very spread apart. And then we found a confidence interval. The confidence interval is just going to be this little band right here. It should be very narrow. That's the whole point of doing our statistics, to narrow down where we think the average is. It shouldn't be as wide as all the actual heights because then it wouldn't give us any useful information anyways. Okay. So your actual individual heights for your population, for your sample, it doesn't matter if it's the individuals for the population or sample, it's going to be spread out quite wide. Your confidence interval by comparison should be very narrow. So you should never have 95% of the individual heights within the confidence interval because the actual heights are very spread out compared to the confidence interval. Last problem. So a pair of dice are rolled. If you get 2 1s, you win $44. Otherwise, you lose $1. And you repeat this game 360 times. Okay, so let's look at a few things. Like it says, how much do you expect to win or lose in total? Give or take how much. Now, this obviously isn't a like population average or population percentages problem. So we're not doing things that we've been doing for the last little while. And so if it's not one of those, but it's still talking about expecting to win and chances and things, we better go back to our box models. Let's see. So for my box model, I would start by saying something like, my total winnings is like the sum of blank draws from the box. Isn't that how it always starts for box models? Okay, so how many draws? Well, we're playing the game 360 times. So we have 360 draws. What is the box going to look like? Okay, well, let's first look at this. we have to get two ones. Well, how likely is it to get two ones versus everything else? Well, the probability of getting a 1 and another 1. Well, the probability of getting the first one is 1/6, and then we'd have to times for the end, and the next one would also be 1/6. So it's 1 out of 36. And so that's the probability of getting a 1, which means the probability of anything else is going to be 35 out of 36, because you always have to add up to 1. So for my tickets then, my box is going to look like this. I'm going to have one ticket, 1 out of 36, one ticket for winning, so I'll win $44. Then you need your tickets for losing. So there's a 35 out of 36 chance that I lose. So that means there'll be 35 tickets with a negative $1. So 1 chance to win, 35 chances to lose. I win $44, I lose $1. So there's my box. When you do things for average boxes, we're looking for how much you expect to win. But first, you have to go back to the box level. So first we have to find the average of the box. So average of the box, you just kind of add everything up. But I would have to add 44 plus -1 plus -1 plus ... plus -1. And have to divide by how many there are. And there are 36. So I don't really want to add up those -1s 35 times. So I could just do this is 44 plus 35 times -1 over 36, because there are 35 of those -1s. So this gives me, put it all into my calculator, 0.25. So that's the average of the box. I can also find standard deviation of a box because there are only two numbers, so that's something I can do. So it's going to be the big number minus the small number times the square root of the fraction of the big times fraction with the small number. Let's see, so our big number in this case is 44 minus a -1 times the fraction with the big number is just 1 out of 36, and fraction of the small number is 35 out of 36, which gives me 7.39. Okay, so we found our box, we found the average, and I saved the box. Now we can find expected value and standard error. So expected value for a sum, because we said it'll be like the sum of drawing 360 times, is always equal to your number of draws times the average of the box. So let's see, 360 times 0.25, which gives me 90. And standard error for the sum is equal to the square root of the number of draws times the SD of the box. So square root of 360 times 7.39, which gives me 140.2. So if you put all that together, we expect to win a total of about $90, give or take $140.20. That's actually very good odds for us. Usually you don't really expect to win a lot. Part B, let's find the chance that your net gain is positive. So saying your net gain is positive, that's like saying find the chance that you win more than $0. Okay, So it's a chance. We were talking about box models. That's going to be a normal curve problem. And you always start a normal curve problem by standardizing. So z is going to be equal to your sum minus the expected value of the sum over the standard error of the sum. If you haven't noticed yet, z is always equal to like the thing you're interested in minus expected value over standard error. Let's see, so the sum we're interested in is 0 minus the expected value, which is 90, over the standard deviation of 140.2. I think that makes sense. So we said that we might expect to win $90, but that's still give or take 140, which means you could still be negative pretty easily. Okay, so this z value is negative 0.64. And we want the area to the right of it because that's a more than. So z equals negative 0.64. We want the area to the right. Looking at my normal table for negative 0.64, this would be the closest. But notice that's going to be the area to my left. I don't really want that, but let's go back and put it on the diagram. So the area to the left is 25.78%, which means then the area to the left I'll subtract from 100%. So 100% minus 25.78% gives me 74.22%. So there is a 74.22% chance we win more than $0. Now, again, if you're going to go gambling and you can find something with that good of odds, that's pretty good. Oh, let's see. Okay, our next one. How many times do you expect to win, give or take how much? Now, when you talk about how many times, that's a counting problem. So we have to count how many times we win. Anytime you count, you're going to change your box so you only have the numbers 0 and 1. So the number of times we win is still like the sum of we're still going to do 360 draws from the box, and let's figure out what needs to go into our box. So when you have a box and you want to count, you do only a 1 and a 0. The 1 is for what you want, so that would be win. And the 0 is for what you don't want, which in our case would be lose. And you just have to figure out how many tickets of each. Well, how many times can you win? So remember up here, we could win with 1 ticket and lose with 35 tickets. So we have 1 ticket for a win and 35 tickets for a lose. But after this point, once we have it set up, we do everything exactly the same. So let's find the average of the box. Well, there's 1 win and there's 35 zeros. So 1 plus 35 times 0 over 36. Because I didn't want to have to add up 35 zeros. This gives me 0.0277. Okay, standard deviation of box. Again, we'll use that formula, which is big number minus small number times the square root of our fraction for the big times fraction for the small. So my big number inside the box is 1. My small number is 0. And there's 1 out of 36 for the 1 and 35 out of 36 for the small, which gives me 0.164. Now we can find expected value and standard error. So expected value, again, is number of draws times the average of the box, which is equal to 360 times 0.0277, or 9.972. And the standard error of the sum is equal to the square root of the number of draws times the standard deviation of the box, which is equal to square root of 360 times the standard deviation of 0.164. So that gives me 3.11. So we expect to win about 9.972 times, give or take 3.11.